Another relatively straightforward thing you can do in SolidWorks is to model just static friction. So this is a pretty traditional problem where you have a block sitting on a wedge, sitting on a floor, and you know the, what do you call that, coefficient of static friction between the two surfaces, and you've got forces on the block and forces on the wedge, and you can pretend the force on the block is, weight or whatever. But we want to solve this, so we'll start by drawing a free body diagram. So we've got the 200 on the top, and from the contact, we've got a normal force, and there's going to be two different normal forces. There's going to be between the wedge and the block and between the wedge and the floor, so I'll call this one N1. And then I'm going to have a frictional force opposing the motion that it wants to move down, and we'll call that F1. And I know that the maximum value that F1 can be is 0.6 times N1, so as long as I get a frictional force less than that, I'll be fine. All right, and now we can start putting together some forces in the X and Y. Okay. Oh my goodness, I forgot to give you some actually important information. Okay, so it's important that you actually know what angle we have here, so we'll just pretend that that's 20. And it doesn't really matter because who cares, we're just doing this for fun. If this is a real wedge and block, maybe it would have some grand reason. But anyway, we can put that 20 degrees in there, and now we can look at the sum of the forces in the Y. So clearly we have a negative 200 pushing down, and then if we're looking at the frictional force, it's also pointing up. It's opposite the 20, so that makes it a sign. And the N1 is also pushing up, so that is going to be positive. It's going to be cosine because that 20-degree angle is now over there and it's adjacent, so it's plus N1 cosine 20, and that's going to be equal to 0. Great. Now we're going to look at the sum of the forces in the X direction. Okay, so we should only have those two forces. Yeah. Okay, so now with the F1, it's pointing in the positive direction, but it's now the adjacent side of that 20 degrees. But the N1 is now pointing in the negative X direction, so we've got minus N1 sine of 20 degrees. And we're going to math, and seriously, if you are having a hard time with two equations and two unknowns, yeah, so statics would be a lot harder. So N1 is 188 and F1 is 68.4. Yay! Now I can start looking at doing the other one. So now I'm going to focus on the wedge. So I found the contact between the wedge and the block, so now I can try to work on getting the contact between the wedge and the floor. Okay, now I have my free body diagram that I'm going to go ahead and get started with. The friction, the F1, is in the opposite direction, and I'm going to go ahead and label it 68.4 because it's equal and opposite, and then I'm going to put in the normal force, and it's going to be 188, and this looks funny. I don't know why, but it looks funny. Oh yeah, that's because it's the wrong direction. Okay, so it's going to be negative or in the opposite direction. So the basic idea is if I grab this here and I throw it on top, those green arrows of the normal contact and the red arrow of the frictional force cancel each other out because they become internal forces. Okay, so now I know I got this right. Then I'm going to put in that 100 Newton force. 100 Newton force. Then I want to look at the contact to the floor, so this will be my N2. And then there's going to be a frictional force opposing that motion as well. So that'll go in the other direction of F2. Beautiful. How exciting. Now I do know that the F2 max again can't be any more than 0.6 of that second normal force. So as long as I get something less than that, I've got a good solution, and I haven't run out of statics. I'm still in statics as long as I can meet that. So the sum of the forces in the Y, we have that same 20-degree angle there, and these are going to just look very, very similar to what we had because they're the same components, but the 188 is pointing down, and it is going to be adjacent to the 20, so cosine, and then, yeah, so right there, so see how it's adjacent to the 20, it's pointing down. Get rid of that. All right, then we want to look at the frictional force that we know of, and it's a 68.4, and that's actually going to be the opposite and sine 20, the rest of the y stuff, just n2, there we go, so that's 0. Now we're looking at the sum of the forces in the x direction. So now in the x direction, that 188 is going to be positive, and it's the opposite side of the 20, so we've got the sign. The 68.4 is still working against us, except now it's a cosine. And we have the minus 100 and the plus f2. And again, we do math, and we get that f2 is equal to 100 and n2 is equal to 200. So this is great, because again, that f2 that I got, which is 100, is still less than 0.6 of the 200, because that would be 120. So as long as I'm less than 120, I'm good to go. So now that we know these values, we can go ahead and put it in SolidWorks and see if we get what we expect to get. So now we're going to go ahead and put this in SolidWorks. Now we didn't actually need dimensions to do this by hand, but I went ahead and put in some dimensions because clearly you'll need dimensions for SolidWorks. So what I've done is I've created a new part. Okay, and what I'm going to do now is I'm going to sketch on the front plane. And I'm going to start at the origin, go up, make sure I got a vertical sign, a horizontal sign, so that little yellow thing, and then down to here. Beautiful. So I'll smart dimension the two sides at 0.1 and 0.1, and I'll call this guy would be 90 minus 20 is 70 degrees. So that's a nice little block, and I'll extrude it again. It doesn't really matter how much I extrude it. 0.01 is fine, as long as I do them all the same. There we go. Now I'll call this, I have to save this as something. Now ideally you want to save all of these into the same folder just so that you can access them and everything's stored a little bit better, but it's really up to you. Now I'm actually going to create a new part. And when I create this new part, again, I'm going to sketch on the front plane, and now I'm going to sketch the wedge. The wedge will start here, and it doesn't really matter if it does, but we'll just make it pretty vertical. Here, I know that the line down here is 0.1, and then here to here is 20 degrees. I got pretty close. Fully defined, exit the sketch, extrude it, and it's going to extrude it to that same 0.01, and that's beautiful. So now I'm going to save the wedge. Okay, now I actually have to create a floor, so I'm going to create one more new part. And this time I'm going to, well, I can just do it on the front plane again. There we go. I'm going to do a center, center rectangle. Okay, center rectangle like this. So basically the whole idea is I just need a floor to attach it to. Since the whole thing is 0.1 long, I'll call this 0.2 just so we have a nice big floor to work from. And again, I really don't care how tall the floor is because it's just a fake floor. And there we go, and I'm going to extrude it, and it doesn't need to be any wider than everything else. Now I'm going to save this as floor, and that's good. All right, next step is I'm going to create an assembly from this part. All right, so I'm going to create an assembly, so all these are still open, so they're all still available, and hopefully it'll work with me here. Sometimes there's a little bit of a delay, so don't get too angry too quickly. There we go. All right, now note that it says F, which means the floor is fixed, which is great because I really don't want my floor to move because it's the floor. All right, so I'm going to go to Assembly, insert a new component. I'll insert a wedge, and then I'm also going to insert the block. Okay. Now there's a couple of things that I can do before I create the simulation, like I'm going to click this guy and this guy. I want the two front planes to be aligned. There we go. If that little pop-up menu doesn't show up, it's just a mate, so you can go to the little paper clip, but it's really not a big deal. Okay, now these are moving. Let's see, what else can I do to make these? Which way are they moving? They're going lefty, righty? Oh, that doesn't make any sense. Whoa, you're all kinds of crazy. There we go. Oh, it's not crazy, it just looks weird. Are you not mated? Because now they shouldn't move left, right, because I just told them not to. Okay, let's try this again. You, thingy. These mates that I keep telling you about, you're ignoring me. So let me delete them, because sometimes with SolidWorks, it's hard to understand why they're stupid, and so the solution is just to redo it. So let's try this again. This guy and this guy must be mated, lefty-righty. Okay, so now these guys move together, lefty-righty. Okay, so now this one and this one, so I'm clicking on, basically what I'm doing is I'm clicking here and I'm hitting the control key and then I'm clicking here. Okay, so now you should be mated to that. Now I should not be able to move you guys, except you're lying to me. That's so weird. I have no idea why it's not letting me do this. Oh, it is. I'm just too stupid to realize that I'm right. So see, whenever I can't actually move it left to right. I was freaking out for no reason. So if you're ever doing SolidWorks at home and you're like, this isn't working, and you're like, she did it in like 6 minutes, it's like, no, I don't think you understand. This 6-minute video is like 7 hours in the making. So it's just moving up and down. It's not really moving left to right. It just looks like it because of, you know, weird stuff. But it's not. Okay, so this guy is going to go back here, and this guy is going to go back here. Okay, now, you're like, well, why didn't you mate this to this? And I'm going to, but I'm actually going to wait until I start the simulation to do that. So I'm going to go ahead and save. And I'm going to call this, you know, assembly. Okay, and then I'll go into the simulation and I'll get that started. So it's just a static simulation. And basically the idea is I want to be able to access these guys, and I can't access them easily once they're connected. So I'm going to talk to the simulation about those connections. So I'm going to establish a contact set. So I'm going to manually do this. So basically I'm going to click this guy, and it doesn't automatically go down to the pink section, so you have to do that yourself. And I'm going to say, hey, check it out, there's friction, and the coefficient is 0.6. So you go, yay! And then I'm going to do the same thing for this one. I'm going to come in here, and I'm going to create a contact set, and I'm going to say, hey, this guy here is connected, touching this guy here, and they have a coefficient of friction of 0.6. And so now once I have that established, I can go through here, click this one, and click this one, and make them coincident. And I can click this one and this one and make them coincident. So, I mean, if they're already coincident, it's just kind of hard to move them and see underneath them. I guess I could have done it, but it's just a little bit, to me, it makes more sense to put that in there before you stick them together. That way you don't forget later. Okay, so now I've got this block moving on this wedge, and SolidWorks isn't very good with contact detection, collision detection, just because it takes up a lot of resources and it's not always necessary. But if I turn it to the side, I see it's exactly what I want it to be. Okay, so the next step is just to add in the forces. So, not entirely. I do need to make sure my floor is fixed. So I'm going to add a fixed geometry to my floor. So now my floor isn't going anywhere. All right, now I can add my forces. So I'm going to add a force to the top right here. And the force is 200. No, except I didn't type it. 200. There we go. You like that? Okay. And then the force on the right. And whether or not we put it on an exact force in the center or just kind of hit the face in general, we're still going to get the same answers. There we go. And this force here was 100. Okay. Sorry about that. My SolidWorks crashed, so I think I've got us built back up to where we were. So anyway, you see that this moves here, and that's just fine. So I don't have to have these mated, but if they're kind of close to right around the right size or the right shape, I don't think you get a different answer, but if you have something that's like super off, like if I had this kind of set like this, that's not going to solve, because if you look at it, you know, it's going to tip over. So it shouldn't matter entirely, as long as you're on the floor and as long as you're relatively well established. I don't like to mate the sides if I don't have to, because I don't want to enforce that connection, although I don't think it's going to care, but I'm just going to go ahead and leave it like this. So now I'm going to apply my favorite material, and I'm going to run the study. And sometimes this does take a while, so if it gets bogged down, just don't cancel. It's probably not messed up unless you did something like leave it hanging off the side. So just leave it and let it hang out. You might have to come back in a few minutes and see what the final answer is, but it probably will solve, and if it won't solve, it'll come back and it'll give you an error. So here I have my solution. I'm going to take off the deformed result because that does add a lot of stress to my poor little teeny weeny computer. I'm going to right click over here on the wedge, and I'm going to hide it. And hopefully it'll go away, except it doesn't seem to have gone away. Hello! Alright, come here. Alright, I'm going to go ahead and list the result forces. Oh, there, it's hidden now. Great. So I'm actually now interested in the contact and friction force. So since this is hidden, I can go in here and I can touch these two sides without making anybody mad or moving anybody around. And I hit update. And what you're going to see here is the normal force. So what I see here is that I have a normal force of 188 and I have a normal force of 200. And those are the exact same answers that we got when we were modeling this by hand. Now you see the two different component reactions. That doesn't matter because remember we drew the normal arrow perpendicular to the surface, and so whenever we found the normal, it wasn't the x or y component of the normal, it was the full whatever you call it thingy, the full magnitude of the normal. So you say, okay, well I got the normal, what about the frictional? I just have to come over here and click frictional, and I get 68.4 exactly, which is really crazy because I've done this like 6 times and every other time I got it, it was off by a little bit. So I had this whole speech prepared for, but you gotta remember it's numeric, and if it's 1% off, that's okay in a lot of situations because it's just numeric, except now it's exactly the right answer. So I'm not sure what to tell you except that sometimes you just can't help being perfect, and that's kind of a thing that we all have to deal with. So, and then over here is this the frictional force of 100, which is the exact same answer that we got the other way. So again, not earth-shattering news that, we're doing the correct thing and the model is giving us the same answer, but it's really cool to kind of experiment with SolidWorks and see that we can solve more. So I can solve this problem by hand, no issues. But if you gave me something that was, infinitely more complicated, it's really good to know that I can just throw it into the computer and get a really nice answer out of it.